So in this lecture we start a new chapter on bounded linear maps. So let's consider two Banach space x and y, and suppose that you have a map M from x to y. It will be said linear if one, for all x and y in x, m of x plus y it's equal to mx plus my. So this is for all x, y in x. And 2, m of alpha x is equal to alpha m of x for all alpha scalar and all x in x. And note that here I need alpha x to be defined and alpha mx to be defined. So in these lectures I will always assume that x and y are Banach space with respect to the same scalar field, which is represented by k, which will be either the real numbers or the complex numbers. So now if I have two Banach space x, y, and on the same scalar field k, and that will never be mentioned again, and I have a linear map from x to y, it will be said, so this linear map will be said to be continuous if for all sequence xn in x, xn converging to some x, this implies that m of xn, which is a sequence in y, converge to m of x. And it will be said, so m from x to y, and again I insist, m will always be linear, so though it's not stated, I only consider here linear maps, which have been defined previously. So if a linear map from x to y, two Banach spaces, is bounded if there exists a finite constant C0 such that for all x in x, the norm of mx, so this is an element of y, so this is the norm in y, this is bounded by constant C0, which is this constant, times the norm of x, so x is an element of x, so this is the norm of x. So m will be said bounded if there exists this finite constant such that for all x, the norm of mx is bounded by C0 times the norm of x. So the first elementary lemma states that a linear map from x to y, where x and y are Banach space, is bounded if and only if it is continuous. And the proof, it's very simple. So assume that it's bounded. Let's prove that it's continuous. So consider sequence xn in x, xn converging to some x. This means that the norm of xn minus x converge to 0. Now, to show that it's continuous, we have to prove that mxn converge to m of x. So this is the norm y. Well, m it's linear, so this is equal to the norm of m xn minus x in y. M it's bounded, so there exists a finite constant C0 such that the norm of my it's bounded by C0 times the norm of y for all y in x. So by this bound, this is less or equal than C0 times xn minus x, norm in x, and this by assumption it's converging to 0. That proves that mxn is converging to mx, and therefore that m is continuous. So the proof it's quite simple. So now let's prove the converse assertion. And we will prove that by contradiction. So assume that m is not bounded. We will assume that m is not bounded, and we will prove that it's not continuous. So we'll find a sequence which converge, but whose image does not converge. So if m is not bounded, this means that for all n, we can find a point xn in x such that the norm of m xn is larger or equal than n times the norm of xn. So now I want to define from that sequence xn a sequence yn which converges to 0. So yn will be xn divided by the norm of xn. With that, I get a vector, an element which has norm equal to 1. Let me divide that by 1 over square root of n. Therefore, the norm of yn, which is equal to the norm of this expression, so norm of xn square root of n goes out of the norm, I get the norm of xn divided by xn, which is 1. So the norm of yn is equal to 1 divided by square root of n, which converge to 0, which means that yn converge to 0. So we have a sequence here, yn, which is converging to 0. However, if we consider m of yn, well, m of yn by definition is m of xn divided by square root of xn divided by the norm of n divided by the square root of n. By linearity, this is equal to 1 divided by norm of xn 1 over square root of n m of xn. Now, if I take the norm on these identities, I get the norm of that, but by linearity of the norm, this is equal to this expression. And by assumption, the norm of m xn is larger or equal than n times the norm of xn. So this is larger or equal norm of xn square root of n xn times n. So you see that the norm of xn cancel, square root cancel with n, and this is equal to square root of n, which does not go to 0. So it's not true that m of yn converge to 0 because its norm does not converge to 0. Which means that if m is not bounded, we can find a sequence yn which converge to 0, but whose image m of yn does not converge to 0. So if m is not bounded, m is not continuous, and that completes the proof of this lemma. So on many occasions, we will start from spaces which are not Banach spaces. So x and y will be only normed linear space. That's usually what happens when we investigate some norm on a space of function. We will start by a space of smooth functions. We will define a norm in that space. That space will not be complete with respect to that norm. We will define an operator or a map in this space X, which is not a Banach space. And we want to complete X and extend the definition of the operator from X to its completion. So what I want to show now is that if you start from a two-normed linear space, and if you start from a map from X to Y, which is bounded, linear and bounded, if you represent by X bar the completion of X and Y bar the completion of Y, what I claim is that it's always possible to extend the definition of M from the completion of X to the completion of Y, and this is what I want to show now. So how to define this operator from the completion of X to the completion of Y with the property that M0, it's still bounded and linear. So fix such space. Remember that X bar, which is the completion, it's formed by Cauchy sequences. So I will represent these Cauchy sequences by Xn. So Xn will be a sequence which is of elements Xn in X, such that this sequence Xn, it's Cauchy. And this is the class of equivalence of this Cauchy sequence. So I will say that two Cauchy sequence, Xn and Xn tilde are equivalent if Xn minus Xn tilde converge to 0. So I'll say that they are equivalent or equal, and recall that the norm of a Cauchy sequence is just the limit in n of the norm of Xn. So this is just to recall you what is the completion of a normed linear space with respect to a norm. So the elements of X bar are Cauchy sequences, so I'll represent these Cauchy sequence by this symbol. So this is a Cauchy sequence. And I'll say that two Cauchy sequence, so once I have defined this new space, so the space of all Cauchy sequences in X, I have to take an equivalent relation. So I'll say that two Cauchy sequences are equivalent if their difference converge to 0. So I'll take, so X, the completion will be, so let me take maybe, call that hat. So the completion will be this space with respect modulo this equivalence relation. And in this space X bar, I will define the norm of this sequence as the limit of the norm of the sequence. So this is just to remind you what is the completion of X. And now I have to define, I want to extend Xm to the space X bar. Remember that, of course, I can embed X into X bar by just considering the elements of X bar which are sequences which are constant. So an element of X is mapped to the sequence which is constant equal to X. So in this way, X bar, it's an extension of my space X. Now I want to define M0 on X bar and to Y bar. So let's consider a Cauchy sequence Xn. And I want to map this sequence to the sequence Mxn. So what I claim is that if Xn is a Cauchy sequence, then M of Xn is a Cauchy sequence. And moreover, that this map is well defined, it's linear, and it's bounded. So I need to check all these conditions for this extension. So let me just ensure that I'm clear. I'm taking an element of the completion. Elements of the completion are equivalent classes. So let me take here an equivalence class of a sequence, of a Cauchy sequence. And I want to define M0 of that equivalence class as mxn, the sequence mxn, or the equivalence class of this sequence. So first, I have to make sure that m of xn is a Cauchy sequence, which means that m of xn it's indeed an element of the completion of y. And then to show that m0 is well defined. So if I take another element of this equivalence class, I get the same result. And finally, I have to show that with this definition, m0 it's linear, it's bounded, and that m0 is an extension, which means that if I take here the constant sequence, the image by m0 of this constant sequence, it's the constant sequence equal to m of x. So let me go step by step. First, let me show that m of xn, it's a Cauchy sequence. So my claim is that m of xn, it's a Cauchy sequence in y, provided xn, it's a Cauchy sequence. But this is clear because m, it's bounded, which means that there exists a constant c0 such that m of y, it's bounded by c0 times the norm of y. Mind that I will always never recall that here we are talking about norms in y and here norms in x. I think the context makes it clear to which norm I'm referring to. So to show that this is a Cauchy sequence, I just have to write that if you take two elements, you consider their difference, by linearity, this is equal to m xn minus xn, and that this is bounded by constant c0, xn minus xm. And therefore, if xn is a Cauchy sequence, then m of xn is a Cauchy sequence. So indeed, this is a Cauchy sequence, and I can consider the equivalence class of this sequence. So this is an element. Now, second step consists in showing that this is well defined, which means that if I take two different elements of the same equivalence class, the image is the same. So let me consider two Cauchy sequences, xn and zn. I will assume that the equivalence classes are equal. So the equivalence class of the Cauchy sequence xn, it's equal to the equivalence class of the Cauchy sequence zn. And I want to prove that m of xn, so the equivalence class of the Cauchy sequence mxn, it's equal to the equivalence class of the Cauchy sequence mzn. So this is the second step. And this is also elementary, because if these two equivalence classes are equal, this means that xn minus zn converge to 0. So what I know is that xn minus zn converge to 0. Since m is bounded, m is continuous. So this means that mxn minus zn converge to 0. By linearity, this means that m of xn minus m of zn converge to 0, and therefore the equivalence class of mxn it's equal to the equivalence class of mzn. Therefore, this map it's well defined. So now we have a map which is well defined from the completion of x to the completion of y. Now I want to show that this map, it's linear, it's bounded, and it's an extension of M. Well, let's first show that M0 is an extension So let's consider a point x in X. Let's consider the equivalence class of the sequence which is constant equal to X. And I want to prove that M0 of X it's equal to Mx, so the equivalence class associated to the sequence which is constant equal to Mx. Well, but by definition, M0 of X, by definition of our map M0, M0 of the Cauchy, the equivalence class of the Cauchy sequence constant equal to X, it's equal to the equivalence class of the Cauchy sequence constant equal to Mx, and this is exactly what we wanted. Therefore, indeed, M0 it's an extension of the original map M. Now, so it's an extension, it's well defined. Now let's prove that it's linear and it's bounded. So let's prove that M0 is linear. So let's consider two equivalence class, the one of Xn and the one associated to the Cauchy sequence Zn. Now, Xn plus Zn. So this is two elements of X bar. I'm taking the sum, and I know that one representative of this new equivalence class is the equivalence class associated to the sequence Xn plus Zn, which is a Cauchy sequence. Therefore, M0 of Xn plus Zn. So here I have two elements of X bar, and I'm saying that the sum of these two elements it's equal to this element. So this is just a property of the completion. Now, by definition of M0, M0 of this equivalence class, it's equal to the equivalence class of M of Xn plus Zn. But by linearity of M, this is the equivalence class of Mxn plus Mzn. And again, by property of equivalence classes, the equivalence class of the sum of these two sequences is the sum of the equivalence classes. But M of Xn, by definition, it's M0 of the, so let me write it here because I have no more space. So this is equal to star, and star, let me write it here. Mxn is M0 of Xn, and Mzn is M0 of the equivalence class associated to the sequence Zn. So what we get at the end is that M0 of this sum, it's equal to the sum of M0 Xn and M0 of Zn. Therefore, M0 has one property of needed in the proof of linearity, and the other one, it's the proof of the other one, it's similar. So I leave it to you to show that if I take an equivalence class xn and I take alpha in scalar alpha, then M0 of alpha xn, it's equal to alpha M0 of xn. So I leave it to you as an exercise to show this second property. And the proof of this second property, it's very similar to the proof of the previous property, which I presented in full detail. So with that, we know that M0, it's linear. And finally, we have to show that M0 is bounded. So let's consider an element xn in the completion of X. Let's consider the norm of M0 of xn. Well, by definition, M0 of this equivalence class, it's equal to M of xn, so the norm of this equivalence class. But the norm of an equivalent class is the limit of xn, so this is equal to the limit in n of the norm of M xn. But since M it's bounded, because we started from a bounded map, this is, so M of xn it's bounded by C0 xn, and therefore the limit of this sequence, it's bounded by the limit inf of this sequence. But the limit of, well, xn it's a Cauchy sequence, so the norm of xn converge, and the limit it's the norm of the limit of the norms is the norm of the equivalence class. So this is equal to C0, the norm of the equivalence class of xn, and therefore M0, the norm of M0 of this equivalence class is bounded by C0 times the norm of this equivalence class, and this proves that our extension, it's bounded, and it's bounded by the same constant. So therefore, in conclusion, the conclusion is as follows. Assume that x and y are two normed linear space, and that we have a bounded linear map M defined from x to y. Then we can extend this bounded linear map to another one, which is defined on the completion of x and takes value in the completion of y. And therefore, there is no loss of generality if we assume from the beginning that x and y are complete. Because if they are not, we can complete them and we can extend the bounded linear map. So for this reason, from now on, I will always assume that x and y are Banach spaces. Now, say that we have two Banach spaces, x and y, and we have bounded linear map M from x to y. So M, it's sometimes called a map, linear map, or also a linear operator. Both terminology are very common. So let's take a bounded linear map or bounded linear operator, M, from x to y. And let's define M, the norm of M, as the supremum for all x in x different from 0, of the norm of mx divided by the norm of x. I leave it to you as an exercise to show that this supremum, it's equal to the supremum over all x in x whose norm is equal to 1 of mx. So I will prove in a few minutes that this defines a norm in the space of bounded linear operators from x to y. But before that, I want to show you the following. Suppose that M it's a bounded linear operator, then its norm is finite. So this is clear because if M is a bounded linear operator, this means that there exists a finite constant C0 such that M of x it's less or equal than the constant C0 times x for all x in x. And therefore, if I take an element with norm equal to 1, what I get from this inequality is that mx it's bounded by C0. And therefore, by taking the supremum over all such x, this is by definition the norm of M. So the norm of M, which is the supremum over all x of norm equal to 1 of mx, this is bounded by C0. So we just proved that if M it's a bounded linear operator, then its norm it's finite. And more than that, if mx it's bounded by C0 times x, then the norm of M it's bounded by C0, which means that M is the smallest constant C0 for which this inequality is satisfied. Let me prove that this inequality is satisfied with the norm of M here, so that mx it's bounded by norm of x times norm of x for all x in x. So let me prove that this inequality holds for all x. Well, for x equal to 0, this is clear because this norm is 0. So on the right-hand side, we have 0. On the left-hand side, since M it's linear, it sends 0 to 0, and therefore M of 0 is 0, the norm of 0. So we have both on the left and on the right-hand side 0. Therefore, this inequality is satisfied. If x is different from 0, then it follows from this identity, since M is the supremum, it follows for all x different from 0 that this quantity is bounded by that, which means that mx, the norm of mx, is bounded by the norm of M times the norm of x, which is exactly what's written here. So what did I prove? I proved that first, if M it's a bounded linear operator, then its norm is finite. And conversely, if its norm is finite, then this inequality is satisfied with the norm of M, C0 equal to the norm of M. And finally, what I claim is that the optimal constant here, C0, is the norm of M. Indeed, assume that this inequality is satisfied by a finite constant C0. This argument gives you that the norm of M is bounded by C0. So let me repeat what we just proved. We proved that first claim, if M is a bounded linear operator, then its norm is finite. This is this argument. And we proved the converse. If the norm of M is finite, then M is a bounded linear operator because this inequality is satisfied. And finally, if you have a bounded linear operator, we know that there exists a constant which satisfies this inequality for all x. The optimal constant which means the smallest constant, is the norm of M due to this argument. So let me represent by Lxy the space of bounded linear operators from x to y. What I claim is that Lxy is a linear space. So I can, if I have M and N elements of L, and I won't write again L of xy, I can define M plus N, which is a new operator, which applied to x, it's equal to M of x plus N of x. And I claim that M plus N, it's a bounded linear operator. And I leave it to you to show that indeed M plus N, it's a bounded linear operator. I can also define, if I have alpha a scalar and M a linear operator, then I can define a new operator, which is alpha times N, and alpha times N applied to x will be equal to alpha times mx. And again, I leave it to you to show that this operator alpha m, it's linear and it's a bounded operator. So with these two observations, we conclude that L, it's indeed a linear space. And what I claim, and I will prove in the next blackboard, is that the norm of M, it's a norm for that linear space. So now I have two Banach space X and Y. L is the space, the linear space of bounded linear operators from X to Y. I wanted to prove that this is a norm in Lxy. So to prove that it's a norm, I have to show that the norm it's always non-negative, and that if it's equal to 0, then M it's equal to 0. Well, that it's non-negative, it's clear from the definition. Now assume that M, the norm, it's equal to 0. This supremum being equal to 0, it means that Mx it's equal to 0 for all x in X whose norm it's equal to 1. But this means that if I take my it's equal y different from 0. So I can, by linearity, rewrite m of y as m, the norm of y times m of y divided by the norm of y. So y divided by the norm of y, it's an element of x which has norm equal to 1. By this expression, since the norm of this element of y, the linear space y, the Banach space y, it's equal to 0, means that this is equal to 0, and therefore 0 times the norm of y is equal to 0. Therefore, we just prove that if y is different from 0, m of y it's equal to 0. And by linearity, we know that m of 0 is equal to 0. So we just proved that m of y it's equal to 0 for all y in X, which proves that m it's indeed the 0 operator, the one which sends any element of X to 0. So now let me prove the second property, that the norm of alpha m it's equal to the absolute value of the scalar alpha times the norm of m for all scalars alpha. So by definition, the norm of alpha m it's equal to the supremum for all x with norm equal to 1 of alpha m applied to x. But by definition of this operator alpha m, this is the supremum of alpha times mx. Now, alpha times mx, it's the absolute value of the scalar alpha times the norm of mx. Since alpha does not appear in the, it's a constant, does not enter in the supremum of this product, it's equal to alpha times the supremum for x with norm equal to 1 of mx. But this is exactly the norm of m, so this is alpha times the norm of m, which is the second property we wanted to prove. So it remains to prove the triangle inequality. So let's consider two operators, m and n, and I want to prove that the norm of m plus n, it's bounded by the norm of m plus the norm of n. By definition, the norm of m plus n, it's equal to the supremum for all x with norm equal to 1 of m plus n of x. But by definition of this operator m plus n of x, it's equal to mx plus nx. Now, by the triangle inequality, the norm of mx plus nx, it's bounded by the norm of mx plus the norm of nx. And now if you take a supremum of a sum, the supremum of a sum, it's bounded above by the sum of the supremum. So this is less or equal than the supremum for x equal to 1 of the norm of mx plus the supremum for x equal to 1 of the norm of nx. And by definition, the supremum of the norm of mx is the norm of m, and this supremum is the norm of n, so this is equal to the norm of m plus the norm of n. So this proves that the third property of a norm is satisfied, and therefore that this linear space with that norm, it's a normed linear space. So we just proved that the space of bounded linear operators from x to y forms a normed linear space with a norm defined by this variational formula. My next statement will be to show that this is a Banach space. So proposition, let's assume that x and y are Banach space. My claim is that the linear space of bounded linear operators from x to y is a Banach space. So we proved already that it's a normed linear space. So what remains to be done is to show that it's complete. So Lxy is complete. To prove that it's complete, we have to consider a Cauchy sequence and to prove that this Cauchy sequence converge. So let Mn be a Cauchy sequence. So this means that for all epsilon positive, there exists n0 such that the norm of Mn minus the norm of minus Mn, it's bounded by epsilon provided n and m are larger than n0. Okay. For my claim is the following. You take any x in X, then Mnx is a Cauchy sequence. And, well, let's prove that. So you fix epsilon positive. By this property, you know that there exists n0 such that if n and m larger than n0, this inequality holds. I will not write it again. So now I consider Mnx minus Mmx. By linearity, this is, or by definition of the operator Mn minus Mm, this is the operator Mn minus Mn applied to X. By an inequality which we proved earlier, this is bounded by the norm of Mn minus Mm times the norm of X. Since n and m are larger than n0, this is bounded by epsilon times the norm of X. And this proves that indeed this sequence Mnx is Cauchy. So what we know up to now is that since our space Y it's complete, it's a Banach space, Mnx is Cauchy, and therefore it converges. So we know that for all x in X, M of nx converge to a limit, and I will represent this limit by M of x. So this defines an operator from x to y in which to each x I associate the limit of Mn of x. So this defines M. So M, it's now a function from x to y. And what I claim is that M belongs to Lxy. So it's a bounded linear operator from x to y, and that Mn converge to M. So these two claims I will prove now. So a claim which I will need in this proof is the following. I claim that the supremum of the norms of Mn, that this is finite. And, well, this is clear. Take epsilon equal to 1. We proved that many times, so let me prove once again. Let me take epsilon equal to 1. So I know that Mn, it's a Cauchy sequence. So there exists n0 such that if n and m are larger than n0, then the difference of the norms, the norm of the difference, it's bounded by 1. So now consider Mn for n larger than n0, then this is, by the triangle inequality, this is bounded by the norm of Mn minus Mn0 plus the norm of Mn0. But since n and n0 are larger than n0, this norm is bounded by 1, and therefore this is bounded by 1 plus Mn0, the norm of Mn0. And this shows that the norm of Mn, it's bounded by 1 plus the maximum from k from 1 up to n0 of the norm of mk. Since each mk it's a bounded linear operator these norms are finite, therefore this maximum is finite, and therefore 1 plus the maximum is finite. And it's clear that Mn is bounded by this quantity. There are two cases. Either n it's less or equal than n0, in which case this norm is bounded by this maximum, or n it's larger than n0, and in this case the norm of Mn it's bounded by 1 plus the maximum. So this proves that this supremum is finite. So up to now we proved two facts. First, that for any x in X, the sequence Mnx converge to Mx, to some converge, and I'm representing by Mx the limit, and also that the supremum of the norms is finite. Now I claim that M is linear. So let me prove that Mx plus y is equal to Mx plus My, and I will leave to you to prove that M alpha x is equal to alpha Mx. So by definition, Mx plus y is the limit of M and x. So this is by definition, this is the limit of Mn x plus y, but by linearity of Mn, this is the limit of M and x plus M and y. So the limit of a sum is the sum of the limits, so this is equal to the limit in n of Mn x plus the limit in n of M and y. And this is equal to Mx by definition of Mx plus My. And this proves that M of x plus y it's indeed equal to Mx plus My. And exactly in the same way, we can prove that M of alpha x it's equal to alpha Mx for all x in X and for all scalar alpha. So we proved that M it's linear, and now I claim that M it's bounded, and by proving that M it's bounded and linear, we will have shown that M it's an element of this Banach space. So B, M it's bounded, and to prove that I have to estimate Mx. I want to prove that this is bounded by a constant C0 times the norm of x. So I want to show that there exists a constant C0 such that for all x, the norm of Mx it's bounded by C0 times the norm of x. But by definition, Mx it's the limit. So Mx it's the limit in n of the norm of Mnx. Right? We have seen that if we have a sequence which converge, then the norms of this sequence converge to the norm of the limit. So we have this. On the other hand, since Mn it's a bounded operator, we have seen that the norm of Mnx it's bounded by the norm of Mn times the norm of x. So for any n, this norm it's bounded by this product, and therefore this limit it's bounded by the limit inf of this sequence. Well, but x does not depend on n, so this is equal to the norm of x times the limit inf of the norm of Mn. And I can, well, and this limit inf it's finite because we proved that the supremum of this norm is finite. So if I call that C0, this is bounded by C0 times the norm of x. And this C0 does not depend on x, so this inequality holds for all x in X with C0 given by this supremum, and that proves that M it's a bounded linear operator, so that M it's an element of this space. So up to now I proved that for any x in X, M and X converge to Mx, and that M it's a bounded linear operator. Now to show that this linear space is complete, it remains to prove that Mn converge to M. Now fix epsilon positive. I know that Mn it's a Cauchy sequence, so I know that there exists an N0 such that Mn minus Mm it's bounded by epsilon provided N and M are larger or equal than N0. So now fix X in X and consider Mnx minus Mx. I have to estimate the supremum over X of this quantity, but before I do that, let me take X with norm bounded by 1 or equal to 1, if you wish. Well, I know that Mx is the limit of M and X, so this is equal to the limit as M goes to infinity of M and X minus Mx. Now if I take N here larger than N0, for M sufficiently large, which means for M larger to that same N0, this quantity, which is bounded by the norm of Mn minus Mn times the norm of X. Okay, and well, we proved already that this norm is bounded by that norm. Here, the norm of X it's equal to 1, so actually this norm it's bounded by the norm of Mn minus Mm. But for all M larger than N0, this quantity it's bounded by epsilon. So what I know is that if I take N larger than N0, this limit it's bounded by epsilon, because for all M larger than N0, this is bounded by epsilon, and therefore the limit it's also bounded by epsilon. So we just proved that for any X whose norm is equal to 1, Mnx minus Mx it's bounded by X. So this inequality holds for all such X, so I can take the supremum over all X with norm equal to 1 on the left-hand side to get the same inequality, but this is exactly the norm of Mn minus Mn. So that inequality gives me that Mn minus the norm of M, it's bounded by epsilon for all n larger than N0. And this is exactly saying that Mn converge to M, right? Because for any epsilon, I proved that I could find N0 such that if n is larger than N0, then the norm of Mn minus M is bounded by epsilon, which means that Mn is converging to M, and this completes the proof that this normed linear space is complete, therefore it is a Banach space. So now a remark. Let me take X and Y Banach space, M a bounded linear operator from X to Y, and let me define N as the points X in X which are sent to 0 by M. So all points X which are sent to 0, and my claim is that N it's a closed linear subspace of X. So let me prove this statement? Well, that it's linear, it's clear, right? If you take x and y in n, this means that m of x is equal to m of y, which is equal to 0, and therefore m of x plus y, which is mx plus my, it's equal to 0. And in the same way, you prove that if x belongs to n and alpha it's a scalar, then m alpha x it's also equal to 0, which means that the space n it's linear. And the fact that it's closed, it's also very simple. Say that you have a sequence xn in n, xn converging to x. You want to prove that x belongs to n, but since m it's a bounded linear operator, it is continuous. This means that m of xn converges to m of x. And since xn belongs to the null space of m, this is 0, and that proves that m of x is equal to 0, which proves that x belongs to n, so that indeed n it's a closed space. So let me call this space n the null space of m. We just proved that it's a closed linear space, and therefore we can define an equivalence relation by saying that x it's equivalent to y if, so x and y in x, if y minus x belongs to n, which is the same thing as saying that m of y minus x it's equal to 0. So I can define that equivalence relation, and I can consider the space x modulo that equivalence relation. And what we shall do in the next minute is to show that if I have a bounded linear operator defined in x, if I define n as, if I represent by n the null space, then I can define now a new operator m0 from x modulo n to y, and this new operator will be 1 to 1 and will be also a bounded linear operator. So this is to come in the next few minutes. So let me remind you the setup. We have two Banach space, x and y. We have a bounded linear operator m, and we represented by n the null space of this operator m. Now I want to define m0 from x modulo n to y. So the elements of x modulo n are equivalence classes. So I take x, for x in x I will represent by these brackets x the equivalence class of x, and I will define this as m of x. So what I claim, what I want to prove, so the statement of this lemma is that m0 defined in this way is a bounded linear operator. So of course the proof consists in first showing that this is well defined, that it's linear, and then that it's bounded. In that proof, I will need to recall you how we defined the norm in this space. So if you take an equivalence class of x, the norm of this equivalence class, it's given by the infimum over all y of the infimum of all norms y for y in the equivalence class x, or y equivalent to x. So the norm of the equivalence class, remember, it's the infimum of the norms of all elements in that equivalence class. So my first claim is that m0 is well defined. because of course I can take two different elements which belong to the same equivalence class, I have to make sure that their image are the same. So take x and y in X, assume that the equivalence classes are the same, so assume that x and y belong to the same equivalence class, so assume that y is equivalent to x, but y equivalent to x means that y minus x belongs to the null space, and the null space is defined as all points such that my minus x is equal to 0, and this means that my is equal to mx, so that indeed my is equal to mx, and therefore in this definition it doesn't matter which element I take in the equivalent class. If I take two elements in the same equivalent class, the image by m of these elements are the same, and therefore this operator m0, it's well defined by this relation. So m0, it's well defined. Now my second claim is that m0 is linear. So let me show that m0 of the sum of two elements, it's equal to m0 of x plus m0 of the equivalence class of y. Well, but we know that if I take an equivalence class and another equivalence class, I sum these two equivalence class, this is equal to the equivalence class of the sum of x plus y. So in particular, m0 of the equivalence class of x plus the equivalence class of y, it's equal to m0 applied to the equivalence class of x plus y. Now, by definition, this is equal to mx plus y. By linearity of m, this is mx plus my. And again, by definition, mx, it's m0 of the equivalence class of x, and my, it's m0 of the equivalence class of y. So we have that indeed these, the left-hand side, it's equal to the right-hand side because we have this sequence of identities. So not only m0, it's well defined, but it's linear. My third claim is that m0 is bounded. So to prove that it's bounded, I need to show that there exists a constant c0 such that m0 applied to the equivalence class of x, it's bounded by c0 times the norm of the equivalence class of x. So now I recalled you how you define the norm of an equivalence class. So the norm of the equivalence class of x, it's equal to the infimum of the norms of y for y equivalent to x. So given x, so you fix x, you consider its equivalent class, you can find an element in the equivalence class whose norm it's almost equal the norm of the equivalence class. So given epsilon, I can find y in the equivalence class of x such that the norm of y it's less or equal than the norm of the equivalence class of x plus epsilon. So, right, because this is an infimum, so given this infimum, I can find one y which is almost equal to the infimum. It's equal to the infimum up to this constant epsilon. So, well, since y belongs to the equivalence class of x, m0 of the equivalence class of X, it's equal to M0 of the equivalence class of Y, but this is equal by definition to M of Y. By definition, well, since M it's a bounded operator, this is bounded by the norm of M times the norm of Y. And the norm of Y, it's bounded by the norm of the equivalence class X plus epsilon. So we proved that the norm of M0 of the equivalence class of X, it's bounded by the norm of M times the norm of the equivalence class of X plus epsilon. And since this is true for all epsilon, I can send epsilon to 0 to get that M0, the norm of M0 applied to the equivalence class of X, it's bounded by the norm of M times the norm of the equivalence class of X. And as we have seen, so this proves, since this holds for all equivalence classes, this proves that M0, it's a bounded linear operator. And we have also seen that the norm of M0, it's the best constant, so the one which optimizes this inequality. So that proves also that the norm of M0, it's bounded by the norm of M. So we proved not only that M0, it's a bounded linear operator, but we also proved that its norm, it's bounded by the norm of M. So now I claim that actually we have here an identity. So we just proved that M0 it's a bounded linear operator and that its norm it's bounded by the norm of M. Now I claim that the norm of M it's bounded by the norm of M0. So to prove that, let me fix X in X. And let me consider the norm of Mx. Well, by definition of M0, this is equal to the norm of M0 applied to the equivalence class of X. And since M0 it's a bounded linear operator, this is bounded by the norm of M0 times the norm of the equivalence class of X. And since the equivalence class, the norm of the equivalence class of X, it's given by an infimum, the norm of the equivalence class of X, it's bounded by the norm of X. Now we have an inequality which holds for all X. The norm of Mx, it's bounded by a constant times the norm of X. And we have seen that the norm of M it's the best possible constant, so that this implies that the norm of M it's less or equal than the norm of M0, and this proves that the opposite inequality, and therefore that actually the norm of M0 it's equal to the norm of M. So let me summarize what we proved. We started from a bounded linear operator. We defined the null space. Once we first proved that this null space it's a closed linear subspace of X. So we consider we define an equivalence classes, so that two elements are equivalent if their difference belongs to the null space, which means if M applied to the difference it's equal to 0. Once we have this equivalence relation, we consider the space X modulo that equivalence relation. And for these equivalence classes, we defined a operator M0 from the equivalence classes to Y by this relation. So we proved that M0, it's well-defined, is actually linear and bounded, and moreover, that the norm of M0, it's equal to the norm of the original operator M. Two final remarks concerning this operator. So remark 1 is that M0 is injective, which means that 1-to-1. So if M0 of modulo the equivalence class of X, it's equal to M0 of the equivalence class of Y, then X, it's equal to Y, which means that M0, it's 1-to-1 or injective. And why is that true? Well, by definition, this is Mx. By definition, this is My. If they are equal, this means that Mx, it's equal to My, which means that X minus Y belongs to the null space, which means that X minus Y, which means that X, it's equivalent to Y, which means that the equivalence class of X, it's equal to the equivalence class of Y, and therefore M0 is indeed injective. The second remark, and my last remark in this lecture, is that the range of M0, so the range of M0, it's equal to the range of M. So let's say that we have Y in the range of M0. So the range of M0, recall the range of an operator L is the space of Lx with X in X, the image of L. So let's say that Y, let's assume that Y belongs to the range of M0. So this means that there exists an equivalence class X such that M0 of the equivalence class X, it's equal to Y. But by definition, this means that Mx, it's equal to Y, and this means that Y belongs to the range of M. And conversely, if Y belongs to the range of M, this means that there exists X such that M of X is equal to Y. But this means that M0 of the equivalence class of X is equal to Y by definition of M0. And this means that Y belongs to the range of M0. So the range of these two operators are equal, and the norm are also equal. And the advantage is now that M0, as we proved, is 1-to-1. And with that remark, I conclude this lecture.